Okay, on to the fundamental theorem of algebra, which sounds fundamental, but it's actually not that bad at all. Don't panic. Okay, so all it really says is that any polynomial function of degree n, where n is greater than 0, so in other words, linear and beyond, right, has at least one 0 in the complex number system. Great, you say. Well, the complex number system covers all numbers, so here we go. This gets us to something called the linear factorization theorem, which says that any polynomial degree n can be written as a product of n linear factors. So if you were looking at y equals x cubed plus 3x squared plus 4x plus 1, then you would be able to write it as the product of, well, n, that is, degree is 3 factors, right? It may be the case, however, that some of these factors could be complex numbers, that is, contain an imaginary portion. They're all complex numbers, technically. Now, in the case of a cubic, if you think about it, because of the n behavior, it is possible that it hits 1, 2, 3 real roots, nice and straightforward, right? It is also possible that it actually hits once and does this, only actually crosses once. So it has one real number root, like let's say that's minus or plus, 3, but then these would be complex roots, so minus some complex number. Now remember, because they're complex roots, just like with the quadratics, right? Now if you think about it, these two linear factors together would make a quadratic, right? And so we know if we have a quadratic that has complex roots, we know that it's going to occur in some sort of, so if this one were a plus bi, then the other one would be a minus bi, because they'd be conjugates, right? Conjugates. And so that's going to be kind of fundamental if we know, for instance, one complex root and they tell it to us, we can figure out the other one. I'm not going to belabor this, but it does mean that if we have a series, so let's say we have x plus 1 times x minus 2, and then let's say for argument's sake, it was x minus I, and that would mean if we have minus I, that's a root at 0 minus I, then the other root must be 0 plus I, right? This is altogether a fourth degree polynomial, right? It has 4 roots. In other words, it always is going to have 4 roots in the complex number system, meaning these two are imaginary roots, which is okay. Now, x plus 1 times x minus 2, and I just want to kind of prove to you that this will end up being a nice, what we'd expect, so we'll call this f of x, let's say, right? That the f of x will end up being a nice, well, fourth degree model that would be unsurprising. So x times x is x squared minus 2x plus 1x, so minus x. 1 times negative 2 is negative 2, right? Now, x plus I, x minus I. These are conjugates, right? So it's going to end up being what? Well, x times x is x squared. X plus I minus, x times I, or xi positive, times xi, and then plus, let me just write this out, plus x times I minus x times I. So the imaginary parts cancel out. Negative I times positive I is negative I squared, which we know is, well, that's x squared minus x minus 2. That hasn't gone away. This is x squared. Let's make this look like plus here. Plus. Right. These cancel. Minus I squared becomes plus 1. So now we distribute this. X squared times x squared is x to the 4th. X squared times 1 is x squared, right? So we've taken the x squared times both of those. Now we're going to take the negative x times both this. Negative x times x squared is minus x cubed. Minus x times 1 is minus x. Then we're going to take the negative 2, multiply by the x squared, and the negative 2 times the 1. Now with a little bit of reworking, x to the 4th minus x cubed, right? X squared minus 2x squared is going to be minus x squared minus x minus 2. So in the end, even though it has complex roots, like we saw in the quadratic when I distributed that out, this ends up being a quartic, right? 4th degree model that has those 4 roots, okay?